Thanks, Jonathan. You get extra bonus points for using the word red tape in the proposal and presentation. Our next presenter is Connor Nogales from Northwest Nazarene University, and he'll be presenting on MakerSat-0, 3D printed polymer degradation, first data from orbit.
Thank you. Hi, my name is Connor Nogales. I'm a student undergraduate researcher at Northwest Nazarene University. And today I'm going to be presenting data from Idaho's first satellite, MakerSat-0, some of the first data we got back from orbit. Oh, baby. Next slide. So, in case you don't know about NNU, NNU is located in Nampa, Idaho, which is about 30 minutes outside of Boise. In case you don't know where Idaho is, Idaho is located right there on the map. Just drive north about 30 miles and you'll get there. So yeah, next slide please. So imagine for a moment that you could put a satellite into space without the high-G launch. Imagine what you could do with that. Imagine what that might do to your structure design, to your material choice, to the geometries on your satellite. You see, satellites are designed to survive two extremely different environments, launch and orbit. During launch, they have to survive upwards of 15 Gs. During orbit, they have experienced 0 Gs. So by default, we have to design our satellites to survive 15 Gs because that's going to be the maximum load. However, if we could avoid the high-G launch altogether, then we could design satellites that are much lighter and much more efficient. And although they might never survive the high-G launch, they're going to operate perfectly while in orbit. And so that's really been the focus of the MakerSat project for the past 5 years. Next slide, please. So this is the overview of our presentation. We're going to start out talking about the motivation we had, then we're going to talk about some of the polymer mass loss measurements, talk about some of the results, some of the lessons we learned on MakerSat-0, and finally we're going to talk about MakerSat-1, our upcoming mission through the ISS. Next slide, please. So you're all probably wondering right now, hey, this sounds great, putting a satellite into space without the high-G launch, but how in the world are you actually going to do it? Well, the answer is we're going to manufacture, assemble, and deploy our satellite all from the ISS. So none of this would be possible without a company called Mainspace. About 2 years ago, they put a 3D printer up on the International Space Station. So the MakerSat concept is to print the structure of our satellite on their 3D printer, to ship our electronic boards to the ISS via a resupply mission. Then to have astronauts assemble our satellite on the ISS, and finally to deploy our satellite from the International Space Station. Next slide. So we set forward, we started working on MakerSat-1, but we started going, after a while we found out that polymers degrade in space, and we realized that we're going to be using a polymer frame. So we decided that if we're going to do this polymer frame, we really need to know how is this polymer going to degrade? At what rate is it going to degrade? Is our structure going to fall apart in the first 3 weeks, or is it going to fall apart over the first 3 years? So we dug through some of the literature, and the experiment that we came upon was the NASA 2 MISSI Peace Project. So this project was a great experiment. It was done, basically they took some various polymers and they hung them outside the window of the ISS. And they weighed them before launch, and they weighed them after 4 years later. And as you can see, there's a lot of degradation on those polymers right there after 4 years. So this is a great experiment. It helped us quite a bit, but it does leave us with some gaps. It only gives you 2 data points on what the polymer degradation is. It gives you before launch and 4 years later. Now we all know that the life of CubeSats is in between those 0 and 4 years, so we need to know what happens in between those 2 data points. So we decided to take a step back from MakerSat-1 and put forth a precursor mission, which we're calling MakerSat-0, which will test the polymer degradation, the mass loss of polymers over time continuously over a couple of years. And so, next slide. So we did exactly that. MakerSat-0 was launched on November 18, 2017. It was launched into a polar orbit from Vandenberg Air Force Base aboard a Delta II rocket. MakerSat-0 featured the polymer mass loss experiment, which was described in the earlier slide. It also featured a radiation particle detecting experiment done by students at a local high school called the high school. Also, it featured the NSL Fast Plus aluminum frame, as well as the NSL, which is near space launch, the NSL EPS and radio, as well as their simplex radio. Next slide. So now I'm going to talk about some of the polymer mass loss measurement and some of the techniques we used. Next slide. So virtually every mass measurement technique that we know of uses gravity as the primary means of measurement. So you have a balance or you have a scale. Those all use gravity. However, when you're in space, your environment is microgravity, so you cannot rely on gravity as a means of measurement. So we looked at this problem for a while, and the solution that we came up with was by using a cantilever beam. You see, cantilever beams have a resonant frequency which corresponds to the mass on the end of the beam. And it corresponds through this equation right here, where E is Young's modulus, I is the cross-sectional moment of inertia, L is the length, M is of course the mass, and F res is the resonant frequency of the cantilever beam. Next slide. So we found some piezoelectric sensors, some piezoelectric cantilever sensors, which are about 2 centimeters in length, and we attached some 3D printed polymer samples to the end of these beams. We then designed an experiment in an analog circuit around them in order to measure these cantilevers' resonant frequency. And how we did that was we had a vibration motor which excited the cantilevers and then produced a sine wave. The sine wave we then ran through a comparator, which turned it into a square wave while maintaining the same fundamental frequency. We then ran that square wave into the capture registers on our microcontroller, giving us a period measurement, and then we could get frequency from that. We then integrated the whole circuit onto a PCB, which is what we flew on MakerSat-0. Next slide, please. So now I'm going to talk about some of the results of our polymer mass loss experiment. Next slide. So we tested 4 different 3D printed polymers. We tested nylon, ABS, Ultem, and PLA. We also had a brass control mass, which allowed us to isolate the effects of space versus 3D printed mass loss itself. Next slide. So this is some of the data that we got back from MakerSat-0. I'd like to draw your attention to these 2 bottom rows right here. So this row right here is the initial mass loss. Nylon had 33% mass loss, which is expected because we know nylon has a large amount of outgassing. Ultem had 2% mass loss, PLA had 0% mass loss. Then in the final mass loss category, nylon had 40% mass loss after 2 weeks, which is 8% additional mass loss. Ultem had over 2 weeks, 15% additional mass loss. Very interestingly, PLA actually had 0 mass loss over 2 weeks. So the ABS cantilever right here, it stopped functioning shortly before launch. So we were not able to get any data back from it. I would also like to note that the initial mass loss of these polymers correlates roughly with the density of the material, which we found quite interesting as well. Next slide. So also, the Colville High School radiation particle detecting experiment, it was successful. We were able to determine when we were in the South Atlantic magnetic anomaly. We got a higher radiation particle count while our satellite was there. So to us, that indicated that it was successful. And I just think it's really cool that some high school students were able to put together a science experiment that functioned properly in space. Next slide. So now I'm going to talk about some of the lessons we learned on MakerSat-0. Next slide. So upon launch, the solar panels on the Y side of our satellite stopped functioning. This caused us to have a voltage discharge over the first 2 weeks of our satellite's life. The battery voltage discharged until it hit 6.5 volts, which initiated safe mode. And our satellite should have bounced out of safe mode and bounced back over here and began operating again. However, due to damage to our battery and charging circuit, it did not. In addition, our satellite battery voltage got so low that it reset our onboard computer. And when it did this, our onboard computer reset to its initial launch state, thus began trying to transmit beacons again, which drained our battery and reset the onboard computer again. Thus it looped over and over again, and that is the state that we are currently in and have been in over the past several months. Next slide. So in addition, MakerSat-0 was the first satellite to be flown in a polar orbit utilizing the Global Star radio. And so as you can see right here, there's not a whole lot of Globestar coverage along the poles. So as a result, we only got about 7% packet reception rate from what we sent out. We only received about 7% of our full packets. However, we did get lots and lots of partial packets. And so we calculated that if we'd have changed our full packet size down from 36 bytes down to 9 bytes, then we could have received up to 90% more packet reception rate. Next slide. So now that I talked about MakerSat-0, I'm going to start talking about MakerSat-1 for the remainder of this presentation. MakerSat-0, or MakerSat-1, of course, will be the one going through the ISS, utilizing the technique described at the beginning of this presentation. Next slide. So I'm really excited to tell you guys that MakerSat-1 is ready for launch. The hardware is all completed. It's all working together. Our frame was actually printed on the ISS a year ago, last August. This is actually a photograph taken by astronauts. It was a really cool experience having that done. In addition, we've been talking with NanoRacks and JAXA to figure out a deployment method, and it looks to be a promising avenue for a deployment method. However, MakerSat-1 does need more funding for upmass and for deployment. So if anyone out there has any ideas, any advice for how we might find that, please come talk to me after the talk. I'd love to have a chat with you. Or if anyone out there just has $50,000 they want to give us, I'd really love to have that conversation. So, next slide. So in sum, we talked about how high-G launches cause our satellites to be over-designed. In addition, we talked about how high-G launches can be avoided. Then we talked about how polymers degrade in space. We talked about some of our experiments and the results we got from that. Finally, we talked about the lessons that we learned from MakerSat, what we're going to do differently on MakerSat-1, what we're going to do differently on MakerSat-1. Then we talked about how MakerSat-1 is ready for launch. Next slide. So this is a picture of our team. We're all, looking strapping and handsome up there. Next slide. Next slide. So I'd like to give a special thanks to Scott Higginbotham and Rex Engelhardt from NASA. You guys helped us out a ton, as well as Jason Dunn and Matt Napoli. You guys helped us a lot. The tieback team, we definitely couldn't have done this without you guys. Jeff Daly, Hank Foss, you guys helped us a ton. We certainly would not have had this project without you guys. Special thanks to all of you guys. So thank you for listening. Does anyone have any questions? Any questions? Yeah.
The name implies it's part of this maker community, is that correct?
Yeah, it is. So the idea that we'd like to do is that someday you might be able to upload your files up to the ISS, and they would be able to manufacture a US satellite with just launching raw materials up to the ISS, and you'd be able to just send your files, software up there. Just kind of the whole concept of having the maker community, that type of thing. Yeah. Yes, it was. Sorry, read that again. Yeah, so the question was, what caused us to get so many partial packets and not a lot of full packets? The reason we believe is because we had an intermittent connection with the Globestar satellite constellation. Anyone else? Yeah.
Two small questions. So the first one is, I'd be interested to hear if you can say any more about the deployment method. And then the second is, do you have an estimate of how much astronaut time it takes to assemble your CubeSat?
Yeah, so your first question, the deployment method, I'm not exactly sure what the details of the deployment method are. You'd have to talk to JAXA and NanoRacks, they know more about that. As far as, what was your second question?
Oh, astronaut time to assemble the CubeSat.
Astronaut time, okay. Yeah, so MakerSat-1 utilizes a snap-together design. So there's no fasteners, no tools, and it can be, if you have the electronic boards in the frame, it can be snapped together in under 5 minutes.
Great, thank you.
Yeah. Yeah. Yeah, so the question was, do we have any data to support the radiation degraded the polymers versus outgassing? So there's a couple of main mechanisms that degrade polymers. So it has atomic oxygen radicals, you have ionizing radiation, and then you have outgassing. And so there was no way for us to distinguish between ionizing radiation and atomic oxygen radicals, just because we're measuring mass. It's really difficult to isolate. So we assumed that the initial mass loss was mostly due to outgassing, and then we said that after that it was ionizing radiation and atomic oxygen radicals. Yeah. Yeah, so we went through bake-out and all that testing, and we did not see a whole lot of mass loss in our polymers. However, they were taken out of that environment when we were testing. We couldn't run our testing while we were doing bake-out and thermal testing. NNU doesn't have the resources to do testing and run our experiment in a vacuum chamber. We just don't have access to that type of testing. So the answer is no, we did not run our science experiment while it was in vacuum. Yeah, in the back.
PLA is well known to absorb water, and your flight data shows no mass loss.
Yeah.
How do you explain that? Because you want to expect it would outgas some.
Yeah, we were very surprised by it too. And we would like to repeat this data again on MakerSat-1. We're actually going to be flying a replica of this experiment after we made some improvements. So we're going to take a look at MakerSat-1 launches. We're going to take a look at PLA again and see if we can repeat the same results. It could be that cantilever was damaged upon launch. I don't know. We're looking to repeat this experiment to see if we can verify these results.
Thank you.
Yep. Right on time? Okay. Thank you, guys.